Hi, I'm Nicolas Pita, a PhD in aerospace engineering, part of the Model Flows group, and today I want to introduce you to one of the tools that we have implemented of flow control using Resolvent analysis. So this work has been published in the Results in Engineering in 2024, and basically what we do is apply this algorithm to analyze different flow databases, such as doing the validation in a classical flow pasta cylinder, but also in a turbulent channel with heat transfer to kind of try to enhance the heat transfer in the wall without penalizing too much the drag. So the algorithm that we're going to use is the Resolvent analysis, as I said before. This Resolvent analysis is based on a forced linear dynamic system, where if we introduce a harmonic forcing, we're going to obtain a harmonic solution. And one of these particular solutions is the one that you can see here on the right part of the slide, where the parenthesis, we're going to call it the resolvent operator. And this operator is going to be used to obtain the forcing and response modes that are going to be the ones interesting to analyze the sensitivity of our system. And well, this operator is created by first applying to a database the SVD plus Cholesky decomposition, and then a second part where we can apply either the classical DMD or the HODMD. In our article, we use a more advanced implementation with HODMD, and this way, as I said, we obtain the forcing and response modes of the system. So again, going back, we have used two different databases, the laminar flow pasta cylinder as a validation and a turbulent channel with heat transfer for further analysis. So with these two different problems, we do the CFD, we obtain the databases, and then we extract each time step, each snapshot as a file that has the different spatial dimensions, but also the velocity. In the case of the channel, we can have heat, the temperature, the nozzle number, etc. We organize this either as a snapshot matrix, concatenating the time snapshots in a dimension and all the spatial dimensions in the other one, or a snapshot tensor, where we have our variables, spatial dimensions, and finally the temporal dimension, depending on the implementation of the HODMD. So the methodology of resolvent analysis needs a calibration. In this case, the resolvent analysis is really sensitive to the tolerance that the quantity of modes that we retain. We have to clear the noise, all the noise that we can of our database. So we're going to use quite large values of the tolerance, but well, it depends on the kind of problem you have, of the noise that you may have in your database. In our case, it is closer to 1 to the minus 2. And then also this tolerance is going to be used for also the cleaning of the modes of the DMD. And finally, in the implementation using HODMD, we also have to calibrate the window size, and this will be around 10 or 40% of the total snapshots of our database. And well, once we have our databases and the calibration of our model, the results that we obtain is, as I said, the forcing and response modes. The most interesting one is the forcing mode, because the areas that have high intensity, we have demonstrated in our article that are the ones that are connected to the sensitivity areas, while low intensity areas are the ones are not connected to this. And we can see here that introducing this high intensity areas a forcing, such as in 2 points, for example, here, we obtain, if we apply to this new database, forced database, the resolvent analysis again, we can see that this this forcing mode has changed, also the response mode, while if we introduce it in low intensity areas, we have no change. This can be seen in this 2D cylinder, where we have our 50 Reynolds number simulation. If we introduce these stabilizers, you can see that the bubble is not broken, so the instability that creates this von Karman Street is broken, disappears. Sorry. If we amplify the red nodes to 60 or even to 70, we can see that maybe some oscillations start to happen on really far on the wake of the flow. But so using this this resolvent analysis, we have delayed the stability to higher Reynolds numbers. So once validated the usage of this resolvent analysis, we also applied it to this turbulent channel with heat transfer, and we can see that with the classical RIP channel, we enhance a lot the heat transfer in the wall, but the drag is also increased quite a lot, even more than the heat transfer. So to palliate this, we want to introduce different geometry changes, and we can see that using the resolvent analysis, we detect different areas that we can introduce cavities around the rib, and we can see that doing this, we can amplify the heat transfer with a little bit less than with the rib channel, but we can also decrease the drag. So this would be like a trade-off of the combination of obtaining better heat transfer, but without the penalization of the drag, by combining the rib and the cavity in the areas that has detected the resolvent analysis. So well, that's the work that we have done with this flow control tool. Thank you for watching, and we have all of our codes are available in the website, so please go there and you can download it. So well, thank you for watching the video.